Hi guys, it's Kate, and this is a quick video where I wanted to take a moment and review one of the problems we saw in class during the first class on numerical approximation. Now, numerical approximation is a bit notorious for giving students some trouble, and part of the reason for that, I think most of the reason for that, is that it's very different from other types of integration. Usually you set up a nice definite integral and then compute its exact value using the fundamental theorem of calculus. But for those functions whose integrals require numerical approximation, that is, either the function itself or its antiderivative cannot be written as a composition of elementary functions, numerical approximation is the only way that we're going to get a handle on the value of its definite integral. We don't know the exact value. All we have in these problems is an approximation and then how close that approximation is. And we don't even know exactly how close the approximation is, because then we'd know the exact value, which I already told you we don't know. But in these types of problems, what you have are an approximation and then what's called a bound for the error, which says that the approximation is definitely not more than this far away from the actual value. So take your time, review these problems, and let's take a look at this particular problem and think through it one more time. Here we have Oscar. He apparently works at a reservoir, and this reservoir has water flowing into it during the afternoon and the evening. And the function that describes how the water is flowing into the reservoir is square root of natural log of t. And this function really works for t greater than 1. That's not a technicality that matters at all to this problem because we are caring about t greater than 1. But note that t is hours afternoon. For us in this problem, while the worksheet says the integral from 2 to 6, I really prefer doing the integral from 3 to 6. Let's talk about 3 p.m. to 6 p.m. So let's adjust that on this problem. So there we go. This is going to be the total amount of water that flows into the reservoir between 3 p.m. and 6 p.m. And obviously this function is not easy to integrate. In fact, its antiderivative is not made of elementary functions. And so Oscar uses a left-hand approximating method using 10 subintervals to approximate this integral. Now in class, I used this 4.494723 value right over here. Even though I didn't have the L10 for the integral from 3 to 6. This is the L10 for the integral from 2 to 6. I can actually update that. This isn't completely critical to the problem, but I'd like to rewrite it so that it actually is consistent. The L10, as I've computed it using Mathematica, is going to be equal to 3.6 and change. So I've adjusted the rest of this problem so that it just makes some internal sense. So the left-hand approximation is 3.69022, and so that means that 369.022 gallons of water have entered the reservoir between 3 and 6 p.m. And the overflow protocols must be put into effect if the amount of water, let's now say, is 380 gallons, over 380 gallons. So we're naturally interested in Oscar's computation. So the first part of this question is, why is it probably not a good idea to ask Oscar for the exact value of this integral? Well, he simply can't compute it, right? It doesn't have an antiderivative that's composed of elementary functions. This is why he's using an approximating method in the first place. Which brings us to part B. Why is it probably not a good idea to ask Oscar for the exact error in his computation? That is, why shouldn't you ask him for the exact value of I, the value of the integral, minus L10, the left-hand approximating method? That's the difference between the value of the integral and his approximation. Well, if he had his approximation and the exact error he was making, then he would be able to find the exact value of the integral, which is unfindable, like we talked about in part A. This is just making sure you conceptually understand what Oscar's problem is when it comes to integrating this function and why he has to use numerical approximation in the first place, and the fact that when you find out how far off he is, what that is an error bound. It's saying that the error is definitely not bigger than this number, not that the error is exactly this number. So A, he can't compute the exact value of the integral. B, he's not going to be able to find the exact error either. What we're going to end up with is an approximation, which we already have, and the error bound. So now it says using the error bound for the error given above for L10, give a range of possible exact values of this integral. Our integral is going from 3 to 6 of the square root of natural log of t dt. Draw this range on a number line. Your range can be too big, but it's important not to give a range that does not include the actual value of the integral. All right, so what is our formula for an error bound in this case? Well, for a left-hand approximating method, the error bound, which you can find on your worksheet here, is rewritten like so. Here it is. I just pulled it off of the previous page. Now that capital M sub 1, that is an upper bound for the magnitude of the first derivative of the function you're trying to integrate. So let's take a look at the function we're trying to integrate, square root of natural log of t, and find its first derivative. All right, here it is. We're trying to find an upper bound for this function. Now, it doesn't have to be achievable, as in it doesn't have to be an exact value that this function actually hits. It just has to be a reasonable number that says that this is definitely greater than this function on the interval. Now, when I say reasonable, that means I don't eyeball this and I say up 10 is an upper bound. No. When I say reasonable, it means that it needs to be the same order of magnitude. Like if it's ones or tens or hundredths or thousands or 10,000s. Similarly, decimal-wise, ones or tenths or hundredths or thousandths. You can't just say, oh, this is definitely less than 10 because this is clearly going to be a fraction and we're many orders of magnitude off there, or at least any order of magnitude that we're off is not a good one. So when we look at this, we say, okay, let's take a look. There's only variables in the denominator, and in order to take a look at the most a function can possibly be, that means we want the smallest the denominator can possibly be. The largest the numerator can possibly be, and the smallest the denominator can possibly be. The numerator has a 1 in it. I can't really change that, but let's see how small we can get the denominator on our interval. So we're thinking about values of t between 3 and 6. Well, that 2t part, the smallest that's going to be is going to be 6, right? 1 over 2 times 3. The smallest t can be is 3. And the smallest square root of natural log of t can be is the square root of natural log of 3 as well. So we can say safely that this is definitely going to be less than or equal to 1 over 6 times square root of natural log of 3. Now, if we don't have a calculator, you might want to go even a step further and say, how can I get a better handle on how big this number is without having a natural log value in there? Okay, well, if we think about natural log of 3 separately, we know that natural log of 3 is a little bit greater than 1, which means that the square root of natural log of 3 is going to be greater than the square root of 1, which is 1. So we can actually safely substitute 1 in down here. And since 1 is smaller than square root of natural log of 3, that means that 1 over 6 square root of natural log of 3 is definitely going to be less than 1 over 6 times 1, right? This denominator here, this denominator down here is smaller than this denominator here, which means that 1/6 certainly bigger than 1 over 6 square root of natural log of 3. So this guy right here, that's going to be our upper bound for the first derivative on the interval. This takes practice. The first time I did this, I didn't breeze through it like this. And this is part of the video where you can go back and think that through again and again and again. What I'm doing here is I'm saying that a number that's certainly smaller but close to square root of natural log of 3 is 1. So if I make the denominator even smaller here, it's going to create an easier upper bound for me to play around with. So 1 over 6 square root of natural log of 3 is definitely less than or equal to 1/6 because this denominator here is actually bigger than this denominator here. Let's put that to use. We know what b and a are, we know what n is, so let's write that out. All right, I put in that 1/6 for the upper bound of the magnitude of the first derivative. We don't care about sign. This is just saying that the maximum distance that the approximation is from the exact value is this. So we have 1/6 times 6 minus 3 quantity squared over 2 times 10. So we have 3/40. That is the maximum distance where we are away from the exact value. All right, so what does that mean? We've been asked to give a range of possible exact values, and we're told from our calculations that our approximation is no further away from the exact value than this. So that means that the smallest of the exact value can possibly be is our approximation minus 3/40, and the largest it can possibly be is our approximation plus 3/40. So there's the interval written down. If you wanted to draw the range on a number line, our approximation goes right in the middle. That lower bound goes to the left and the upper bound goes to the right. Now you kind of want to figure out whether Oscar should put the overflow protocol into effect. If we wanted to know whether it's remotely possible that the amount of water is over 380 gallons that's come in, well, we need to figure out what this number is and what this number is. This is not going to be a problem because this is definitely not near 380, but this one could be above 380. Like if 380 lays in here, then we should put overflow protocols into effect. If it's not, then we can say, okay, no overflow protocols. What we're asking in terms of this problem is, could I be equal to 380 or 3.8 in the context of the units of this problem? Could I be equal to 3.8? If it could, these are all the possible, this is the possible range for I. So we want to know if 3.8 lies in here, basically. It normally freaks students out to not have a calculator, but it's going to be okay, because imagine 1/20th is 0.05, which means that 1/40th is 0.025, which means that 3/40th is 0.075. So if we took 3.69022 and we added on 0.075, we'd have 3.76522, which is telling us that the exact value of the integral, which is the exact amount of water that came into the reservoir, is definitely not going to be greater than 3.76522. There's no need for him to use the overflow protocol. Now I want to take a look at the second type of question that's quite typical for a problem like this, which is saying instead of what's the range that the exact value falls in given my approximation's accuracy, the other type of question is, okay, I want a particular level of accuracy. How many slices should I use? So this question is saying, suppose we want to approximate, let's keep it at the integral from 3 to 6 of square root of natural log of t dt. 3. And we want error to be less than 0.01. So it says, using the bound for the error, find a value of n for which you can be sure that your approximation is within, it should say 0.01 of the integral's value. Now we want to start off with the exact same error bound formula, but now what we're trying to do is find an n so that this exact error, which is definitely less than this, needs to also be less than 0.01. We'll use the same bound for the first derivative, the same bound for the integrals, interval 3 and 6, and then solve for n. So what we're looking at here is 1/6 times 9. 2n is still living in the denominator, and I'm going to write this as 1 over 100, just for ease, computational ease, so to speak. If we solve for n, what do we have? This says that n should be greater than 75. This makes sense. This is saying as long as you use at least 75 slices, you'll be this accurate. If you use 100, that's great. If you use 150, that's great. This question is saying, is n unique? No, there's not just one value for the number of slices you use that ensures this level of accuracy. It's literally any value for n greater than 75 will work. But if you go to 74, you're no longer guaranteed that you'll be within that level of accuracy. If you set up this inequality in the wrong direction, you will get a result that makes no sense for you down here. It'll say n should be less than 75 slices. Well, there's no way that it would make sense to ensure a certain amount of accuracy by saying, hey, use less than 75 slices. No, you want to say use more than this number of slices. The more slices you use, the more accurate you get. So there are actually like an infinite number of possibilities that you could use, but there's this lower bound that you're looking for that says the number of slices you use has to be at least this big. So if you ever get to the last part and you suddenly have a statement that says n should be less than this number, something's gone wrong. You probably started off with the inequality in the wrong direction up here. So that's always something good to look out for as a way to check yourself and your reasoning. Anyway, I hope this video was helpful for you, and if you have any questions, don't hesitate to ask. Thanks, guys.